So now we're going to talk about virtual memory. This is chapter 9 in the textbook. This is just an outline of the various topics that are covered in the course in this chapter. And we're going to start by talking about what the benefits of a virtual memory system are, and then we're going to look at how we can realize virtual memory through demand paging, page replacement algorithms, and how we can go about originally allocating frames to processes when they first get started. We'll also talk about thrashing and how we can try to ameliorate the problems of thrashing through use of the working set model. One of the things to consider with modern programs is that a lot of the code that comprises a program is intended for relatively rare events. So special error conditions, you may have a very large data set, but you actually, during the execution of a program, you may only use a tiny portion of it. So if we really want to try to optimize the use of our RAM, a limited resource that we have, then we would like to only bring into the actual RAM the portions of the code and the portion of the data that we actually need to use when the program is running. If we could do that, then that would allow us to have more programs, more processes resident in RAM at the same time. We could increase our degree of multi-programming and keep our CPU busy and get more done basically over the same amount of time. So if we want this to happen, of course, then we need some way to execute programs that are only partially loaded into memory, the rest of them sort of sitting on a hard drive someplace. And what would we do about that? So this is kind of the concept of virtual memory. It's the complete separation of the logical address space or logical memory from the concept of physical memory. And the way this is typically done is we have some of a process's content is going to be stored in the RAM, and others of that process are actually going to be stored on the hard drive. And then there's going to, of course, we're going to need a dance to do in order to bring portions of a program from the hard drive into the RAM, and sometimes to go the other way, portions from the RAM to go back onto the hard drive. But if we're careful about how we do this, then this is going to allow us to have logical address spaces that are much larger than the physical address space. And with modern PCs, like you have, maybe you've got 4, 8, or even 16 gigabytes of RAM in your machine. But through virtual memory, you can actually have a logical address space which is much larger than your physical space. So I think, for example, on the Macintosh I'm working on right now, I think I have 8 gigabytes of RAM, but I think the virtual memory is someplace around about, I think about 80 or 90 gigabytes. So it's a much larger virtual space than I actually have a physical space. So that obviously can be very useful because we can run basically bigger executables and have them resident in memory at the same time, which is very useful. So we're going to look at we're really going to be looking at, there are two techniques that the book talks about: demand segmentation and demand paging. We're going to spend almost all of our time talking about demand paging, though. So here's kind of a graphical representation of what this might look like. So over here you've got virtual memory, so your various, all the different pages that you have in memory. We're going to have a memory mapping scheme that we're going to look at, and somehow the pages are going to be mapped over onto physical memory. And some of the pages you can see, like this page over here, actually does reside in the RAM, in the physical memory, so that's okay. But this page down here, whatever that page was, the memory map here says, oh, that page is not currently stored in memory, it's sitting over here on a hard drive someplace in a sector. So the trick is, how do we know which pages or virtual pages are written on the hard drive and which pages actually are resident in our physical memory? Usually, in almost all operating systems, the logical address space, the virtual address space for each process is arranged in this structure, where you have in the low order physical addresses, in the low order physical address, or sorry, logical addresses, you have your code, because that's typically not going to change, so it'll reside in those low order logical addresses. Then you're going to have your data. There, this is kind of the static data that's first loaded when the program is loaded in. Up at the top, we've got our stack. So this is where whenever a procedure call is made, we have to store all the register values on the stack. We have to store the values of the local variables in a function. They all have to be stored in the stack. And the stack will basically move from the maximum address down. So as we add things onto the stack, this region is going to move down in this direction. We also have the heap. That's another variable size chunk of memory that a process needs to use. And so basically in a Java program, whenever you call new, whenever you're allocating an object, that's coming from the heap. So the heap is basically growing in the other direction, or growing in size. And so of course you're okay for your process can continue to run until basically the stack or the heap bump into each other. At that point, you've reached the maximum size that that process can be and still run in the system. Then one of the nice things about using a virtual scheme like this is that it's going to let us work with sparse address spaces. That is where I have large virtual addresses, but a lot of the virtual space isn't actually being used. So you have lots of holes, and that will make it hopefully easier for us to have multiple processes kind of interleave the holes, their usage of the different pages and frames in the system to make things to work better for multiple processes simultaneously. I'm going to skip over the shared library to sort of basically point out here that if you have a shared library, then the library can sit in a set of frames, and what's being shown here is I have two different page tables over here, and both of them are referring to the same set of pages. So this is just one of the benefits you get with virtual memory. So you don't have to have the same shared library occupying two or more sets of frames. You can use the same frame multiple times. All right, so as I said before, we're not going to worry about demand segmentation. You can go ahead and look that up in the book. I am going to talk about demand paging, though. I will just say as a preamble that most modern operating systems use kind of a mix of paging and segmentation. And so you do need to understand how segmentation works and how paging works, and you probably ought to consider a mix of those things. So you might have a segmentation system where the segments are actually stored as a series of pages, for example. It's one common theme in modern memory management. But anyway, so back to simple, pure demand paging. So the basic idea here is that we call it demand paging or pure demand paging in the sense that we only bring a page from the hard drive onto a frame in memory when we actually need the page. We don't try to predict when that would happen. We don't load any more pages into RAM than we have to. We just wait for a request for a certain page to occur. That is, you get an address in memory which references a page which is not already in the RAM. And when that happens, that means we have to go out and get it from a hard drive and swap it into RAM. There are pros and cons of doing this. In general, it means that you're not doing any unnecessary I/O. You're not bringing in pages more frequently than you absolutely need to. You're kind of using the least amount of memory you could, the least number of frames you might possibly need to store a process, and it can work pretty well. One of the problems with it is that lots of times the CPU is sitting idle, not really doing anything, and while it's not doing anything, it might very well behoove us to go about and load in some pages from the hard drive into RAM, kind of in a predictive fashion, and then if we'd come about needing that page in the future, we wouldn't have to do the load again. But that's maybe getting a little bit ahead of ourselves. So we'll just stick to demand paging. Whenever you need a page, you check to see if it's in the RAM, and if it isn't, we go and get it. One of the ways that we can do this, when we go to we'll look at the page table, we're going to basically somehow in the page table we have to mark whether or not the corresponding page is in RAM or is still on the hard drive. We actually have two things we have to watch out for when we access the page table. It could be that just that the page is valid but it's not in memory, so that's called a page fault. We have to go get it. It could also be that the page that we're trying to access is invalid in some way. For example, it may have been that the operating system said this process only gets to use 10 pages, and one of our addresses is trying to reference page number 11 or 12, something like that. In that case, that should be an invalid page number, an invalid reference, and that should cause some kind of an abort. So here's the basic idea where you've got, again, in our diagram taken from the book, you've got on the hard drive, you've got a whole bunch of pages that are sitting on the hard drive. In this case, the number 0 through 23. One of the things that we will talk about in a little bit is swapping out and swapping in. So when we swap out, that means you're going to take some of the pages that belong to one program, like program A, and you're going to move them from the RAM back over here onto the hard drive. That's a swap out. A swap in goes the other direction. So over here could be that program B, during its execution, needs to access 3 pages that are not currently in memory. And so we'd have to go get those pages from the hard drive and move them onto frames on the memory and update our page table appropriately. So what we'll do with our page table, we'll augment a little bit. So in the previous chapter, our page table really just consisted of this stuff on the left-hand side here. It was just a series of frame numbers. Now we'll do, with each frame number, we're also going to provide an extra bit, a valid, invalid bit. And basically there's going to be one bit, maybe more, you actually may need a couple of bits here, but what we're going to do with this space here is we're going to set the values equal to I, which simply indicates that the particular page is not yet loaded into memory. That is, whatever's in this frame number here is bogus, because this is an I. It's an invalid frame number because it doesn't have a frame yet. We haven't brought it into memory. So if it's a V, if the value of a bit is set to V, then that means that the corresponding value over here, the frame number, is accurate, and that is the frame at which that page is stored. So if you do a reference to your page, use the page table, you're doing a reference, and you find that the corresponding bit for that page is I, that's a page fault, and we need to do something about it. And so here's just another example, another diagram taken from the textbook, which shows the logical memory, the different values that comprise that logical memory. You can see over here, here's the physical memory on the right-hand side over here. You can see that actually only 3 of the pages of our process are currently loaded into the RAM, are currently resident. So just pages A, C, and F. That's page 0, page 2, and page 5. And if you look over here in the page table at 0, 2, and 5, you'll see that their invalid bit is set to valid for only those 3 pages, and the other 3 page values are set to I, meaning they're invalid, so they're only sitting over here. Those pages are only over here on the hard drive. Okay, so what do you do when you have a page fault? So we have an invalid bit, we have a page fault, we've got to go ahead and do something about that. So the first thing is you double check, make sure the page reference is actually legal, and if it isn't, then you throw in a abort, but otherwise it's not in memory. So now you need to locate an empty frame. There's a frame that's not currently in use by another process, and then we have to go ahead and basically start a process to swap the page from the hard drive into that frame. And once that's done, then we will reset the page table to indicate, we have to sort of update the page table so the correct frame number is now there for our page, and we have to set that validation bit to V, and then we have to restart the instruction because the instruction failed when it was first running. We have to go back and start over again, try to re-execute it. All right, now in the worst case, you start a process, you have no pages in memory. That's pure demand paging. And so what's going to happen is you're going to get a lot of page faults when the program first starts executing because you have no pages resident. So pretty much most of the first instructions that are going to be executed are going to call page faults. You'll be swapping in a bunch of pages, but eventually you'll get a bunch in there. It turns out that we have this concept of locality of reference. That's this term over here. And what that means is that in general, and we'll look at working sets later on to see how this works out, but in general, when a program is running, it tends to run in a certain kind of block of memory, and those memory addresses tend to be fairly close to each other. So for example, if you have a program and it's iterating over the elements of an array, then it stands to reason the array is going to be stored typically in contiguous areas in the memory of the machine, and so they'll be stored within 1 or 2 pages, and so you won't have many pages. You'll have initial page fault when you're bringing that array into memory, but then not many page faults after that. So that tends to help out. Now, if we're going to use demand paging, then we're going to need some help from the hardware. We're going to need, this will be in the memory management unit, we're going to need a quick way to do something with the valid invalid bits, because if the valid invalid bit is invalid, then we need some kind of a trap or an exception to occur from the MMU, which will cause the CPU to pay attention to it. We're going to need secondary memory, so we're going to need a swap device like a hard drive, something like that. So we're going to need the hardware support to work with that. And we're going to need some way to cause an instruction to basically restart from where it was. Kind of think about it. Typically, the fetch execute cycle in CPU is you fetch the instruction and you execute it, and part of that execution is you actually move the program counter to the next instruction in the memory. We need to kind of unwind that now because we're going to have to move the program counter so it's back pointing at the instruction that caused the page fault to occur in the first place. You might want to consider, by the way, when we're restarting instructions, it can be difficult for some instructions which are kind of relatively heavy duty. If you had an instruction that did a block move, that is, it moved, say, a large section of memory, maybe it's moving like 1,000 bytes from one location to another, consider if those 1,000 bytes actually happened to span 2 pages. So from the chunk of memory might go from, say, the middle of one page to the end of that page, and to the start of the next page to the middle of that next page. So what would happen if we're in the middle of doing that block move, and all of a sudden we kind of get halfway through, and now we need to switch from one page to the second, and we have a page fault? Well, that obviously could be a bit of a mess. And so I'm not going to go into too much detail about this. It's just enough to understand that there could be some complexities in restarting an instruction that maybe kind of already got halfway through execution before the page fault occurred. All right, so here's a nice diagram from the textbook which kind of shows the major steps of handling a page fault. So here we have an instruction which is, load something from memory, and so that we have some particular address M we're trying to access. That's our reference, and we go to M's address, and we go to the page table, and oops, the page where that value is stored has the invalid bit is set, so that should cause a trap. So we zoom over that causes a trap. We then an exception. We go over to the operating system. The operating system has to then file for the page to be loaded from the hard drive, from what's called the backing store if you're old-fashioned. So you have to do a hard drive access, get the page, bring the page from the hard drive, put it onto a free frame. It'd also be some overhead here of actually identifying a frame that was free. Load it in there. Then we would update the page table to indicate that that page is now properly stored in a frame. And then we would go ahead and restart the instruction, and hopefully we wouldn't get a page fault from this too. Keep in mind that some instructions may have 1, 2, maybe even 4 pages might be referenced in a single instruction. That is, an instruction might consist of up to 4 addresses might be part of it, depending on how complicated your machine language is, and you could get page faults on all of those. So it can get pretty hairy, actually, depending on how complicated your machine code instruction set is. Now, actually, there's a lot more that's going on. The slide's got a lot of text on it. In the previous diagram up here, we kind of left out a lot of details that could have happened in terms of, well, you have to file for an I/O, you have to register an I/O event that has to occur over here, etc. So let's kind of go through these in a little more detail. So you get a page fault. That causes a trap. And so, of course, as part of any trap handling, you have to save all the registers of the current process in the process state. Now the kernel takes over. It looks at the interrupt, determines that the interrupt was caused by a page fault. Then you have to look at, well, was the page fault, did it occur because the reference was illegal? And if it was, that'd be a different error condition. But if it was legal, that just means the page isn't resident in the RAM. It's not in a frame yet. So then we have to determine, well, where is that page stored on the disk? You have some table or something where that's there. And then you have to issue a read operation, a read request to the disk, to go ahead and get that page and load it into the frame. Now, of course, it may be that the hard drive is being used by another process, so there could be a queue that we have to wait for this request from the kernel to go through, so that may take a while. Then, once we are at the head of the queue for the hard drive, we have to wait the normal overhead for accessing the hard drive. There's some kind of we have to wait for the seek time, we have to wait for the latency time, we have to wait for the transfer of the page across the bus from the hard drive. All that can take a fair amount of time. While we're doing that, so while that I/O operation is going on, the CPU might as well go ahead and allocate some cycles to a different process. So that process will go ahead and continue on, but eventually the hard drive will register an interrupt saying, hey, the page got loaded into the frame like you asked. Then we have to suspend this process, which is currently running, our other process, reload the registers in the process state from our original process. That's all this stuff. the disk interrupted us, update the tables, then wait for the current process to come back around. When it's on, take it off of the I/O wait queue, put it on the ready queue. Eventually it'll be its turn on the ready queue, it can run into play, and now it can go on and run again. So there's a whole lot of overhead, obviously, that goes on when a page fault occurs. We can actually try to represent to calculate the average cost of accessing a page if we have a page fault. So let our variable p here represent our page fault rate. So if p is 0, that means there are no page faults occurring at all. If p is 1, that means every single memory reference we make requires a page fault or causes a page fault to occur. So then our effective access time is going to be 1 minus p. So this is the proportion of the time where we don't have page faults. And in that case, the access time is just whatever it would normally cost to access our memory. Then see the same kind of calculation we made back in the previous chapter, in chapter 8. If, however, there is a page fault, so that's proportion p over here, then the total time it's going to take to do the page fault, we're simplifying here a little bit, there's going to be some overhead for the page fault to occur. That's the exception gets thrown, we got to save all those registers, switch to the kernel so it can do some stuff, and then we have to pay the cost for actually accessing the hard drive and bringing the page into memory. Then there's some more overhead for actually restarting. It's another exception we got from the page, from the hard drive, and then we had to, do the stuff with updating the page tables, etc., etc., etc. And then finally, all that's done when the process finally gets running again, then we still have to pay our costs for the memory access, whatever that would normally be. Now, we can actually simplify this equation a great deal, because it turns out that this value over here, the swap-in cost, is going to be way, way higher, several orders of magnitude larger than any of these other values. And here you're probably talking like 8 or 9 milliseconds, where all the rest of these are in microseconds or even nanosecond time frames. So we can really simplify this a lot by dropping out all these lesser terms over here. And then so our effective access time becomes basically, when we don't get a page fault, the normal cost for memory access, plus p, whatever the proportion of the page faults is, times how long it takes us to get a page from the hard drive. So here's a simple example doing that. So let's assume that our memory access time is about 200 nanoseconds. Our average page fault service time is 8 milliseconds. Remember, keep track of the time units here. That's important. We got milliseconds over here, right? Milliseconds and nanoseconds here. So for our plugging into our formula up above, so 1 in p, so this is 1 minus p, that's the proportion of the time that we don't have a page fault. We're just going to pay for our normal memory access time, 200 nanoseconds. But for the other time, when we do have page faults, it's going to cost us 8 milliseconds, or converting it to nanoseconds, 8 million nanoseconds. So that means that our access time is, our effective access time is going to be 200 plus whatever proportion is times this great big number, 7,999,800. So if p is just 1 in 1,000, 0.001, then our effective access time is actually 8.2 microseconds. Well, that's 8.2 microseconds. That is 40 times bigger than our standard 200 nanosecond access time. That's a lot bigger. So even though the page fault rate seems very small, only 1 in 1,000, it means that our program is actually going to be running, it's going to take 40 times longer to run than it would if we weren't using paging at all, if we just had the whole thing sitting in memory and thus no page faults whatsoever. If we wanted our performance degradation to be less than 10%, then basically we have our same formula over here, replace EAT here with a 10% increase, so go from 200 to 220, and then go ahead and solve for P. And what you'll get is that P has to be this little tiny fraction over here, meaning we need the page fault rate to be not more than 1 in every 400,000 memory accesses in order for our performance degradation to be less than 10%, which seems pretty amazing actually, but there it is. Okay, so there are some ways that you can optimize demand paging. You can choose to basically bring a whole bunch of pages into memory kind of all at once, and that cuts down on the number of page faults that are going to occur. And that is used in some older systems. You can also do when we're talking about paging out later on, there's things you can do with paging out or swapping out that will, again, minimize the number of page faults that can occur. Okay, so what happens if there's no free frame? So you have a page fault, you want to bring a page back into memory, but there's no free frame. That is, all the frames are occupied. All your memory is filled by other processes' pages. In that case, you're going to have to choose a page to swap it out. That is, move it from its frame and put it back onto the hard drive. It's a little more complicated than that because you actually don't need to copy the frame back onto the hard drive if there hasn't been any change to the frame since you brought it into the frame from the hard drive. In that case, there's no change. You don't need to swap it out. You can just overwrite it. No harm would be done. Okay, so we need a way to identify which pages are going to be replaced, and we need also a way to keep track of which pages need to be swapped out. So what we'll do is whenever we make some kind of a change to the contents of a page that's resident in a frame, then we're going to have a little bit associated with that. Again, we can put this in our page table, and we can set that bit to true, indicating that the value of the page sitting in the RAM in a frame is actually different from the value of the page that's sitting on the hard drive. So if you do that, now we know when we actually have to swap a page out, instead of just sort of ignoring it and overwriting it with a new page. All right, that's kind of what this diagram shows here, again, taken from the textbook. So you can see we've got two processes running here. You've got one for user 1, one for user 2. They each have a set of pages over here. Some of them are not resident in memory. So for user number 2, page B here, it's page 1. Contents are B. They're sitting over here on the hard drive. They haven't been changed. Over here, though, for this guy, for the user 1, this page over here, M, is sitting over here. It's on the hard drive, but if you look here for process 1, it's page table over here. So that's page number 1. Here's the page table over here. Page table 1 is going to be this guy here. That's number 4. And you can see that the V bit is set to V, so it should be existing in memory. So that guy's okay. So he's sitting in memory, but it looks like it's gray here to indicate that it's dirty. We've made some kind of a change to it. Over here is B. For process 2, you can see page 1, that's this entry here in its page table. The invalid bit is set. That means that that value, that page, has not yet been brought into memory. So at some point we're going to have to bring that in. And if you look at the physical memory, you can see basically all of our pages are occupied. So I should say all of our frames are occupied. There's no free space. So what we can do is we can say, well, we're going to have to get rid of, in this case, say M. We're going to have to swap that out to the hard drive so we can make room for B to be brought into that same frame. And in that case here, we have to go ahead. We have to update this value here. Mark this as an I because it's invalid. We've swapped it out, and we change this to a V, and we can change this number here, this frame number. Then we go to frame number 4, and you'd be okay. Okay, so basic page replacement. So if there is a free frame, go ahead and use the free frame. If there isn't, we have to select a victim frame with some process that we need to write out. And the decision about whether to pick a victim might depend on whether or not that that page has been altered while it was in memory. So here's what we're going to do. There's basically, the problem now is that we may have up to 2 different page transfers we have to do, because if we have to swap a page out, we have to pay the cost for writing a page out to hard drive, and we all still have to pay the cost of bringing the page we needed in the first place from the hard drive back into the frame. So things a little bit more expensive. So our algorithm gets a little more complicated, or I should say our formula for calculating the effective access time is more calculated because we have to add this extra term up here, this T swap out, the cost of swapping out, as well as all the cost we had before. So we have to add sort of another variable. So we'll look at variable M here. M is the modification rate. That is, what portion of the frames of the pages that are sitting in frames have been modified since they were swapped in. So if it's 0, that means that none of the pages have actually been modified. That is, the copy of the pages that sit in memory are exactly the same as the copy of the pages that's sitting on the hard drive. If M is 1, it basically means that every frame has been altered in the RAM since it was swapped from the hard drive into a frame. So our calculation, a little bit more complicated now. It's basically the same formula we had before. We're bringing in M. So again, as before, if there's no page fault at all, that's this 1 minus P portion up here, then the effective access time for memory is just going to be the normal memory access that we calculated back in the previous chapter. However, for the portion of time that we do have a page fault, then we've got this parenthesized expression over here, sort of a sum of values that we have to add on. So again, we have our overhead values we talked about before, the cost for throwing a trap and the saving the registers and all that stuff, looking at page tables, all that. In addition, we still have our swap-in costs. We're going to have to pay to swap in no matter what. And then M proportion of the time that page that we're removing, that we're swapping out, has been altered. Only then, for that portion, do we have to pay this amount of time. If the page has not been altered, then we don't have this T swap out term. It all goes away. Again, we simplify because the swap out and the swap in costs are many orders of magnitude bigger than these other lower values over here, these overhead values and the memory access costs. So we'll just simplify those away. And so what we get is our effective access term becomes this value down here. So 1 minus P at the time, no page faults, just pay the standard memory access cost. But the other time, you do have page faults, and some of the time you got to pay to swap out, but you always have to pay for the swap in. If I go ahead and plug in some numbers into that formula, such as we have here, so suppose our memory access time is very slow, 1 microsecond, and suppose that our page swap time is 10 milliseconds, which is also fairly slow. That's 10,000 microseconds. Remember, you want the units of measurement to be the same. Suppose that 50% of the time the pages being replaced has been modified. So that is M is going to be 0.5. If you go ahead and plug the values into our equation, then you can see that our effective access time becomes 1 plus this 14,909 times P, whatever our page fault rate is, microseconds. So if our page fault is 1 in 1,000, then our effective access time becomes almost 16 microseconds. So we've gone from, if we had no paging at all, from 1 microsecond to 16 microseconds, so a 16-fold increase in our access time. So our program is going to basically run 16 times more slowly than it would if we weren't using a paging system. If you wanted the decrease to be, or the increase to be less than 10%, you could go ahead and just plug in over here on the EAT side over here, change this to be 1.1 microseconds, plug it all in, do the math, and you'll find it again that you basically need a fault in about 150,000 references. You need the page fault rate to be not any more than that. So pretty stiff requirements.